Okay, let's go ahead and get started. I apologize. I'm like sort of starting to lose my voice again. 'Cause, it's only been a week since the last time I had a cold and lost my voice. So I'm not going to speak quite as loudly this time. So we can all be very quiet and it'll be dramatic and very exciting. But you should feel free to move closer if you can't quite hear me well enough. Just a few administrative details. Several people have asked for extensions on the problem set, so I think what I've decided to do is just give everyone an extension until next Tuesday at 3:30. Given that, I think I'm not going to hand out another problem set right now. I would rather have problem sets reflect the reality that apparently now problem sets take a week and a half. So what I'll do is next Tuesday, I'll hand out another problem set, or not me, but the person who is here in my place will be handing out a problem set. And I'll probably just go ahead and give you a week and a half on that, maybe. Maybe I'll do that. Let's see. Next, I guess I could do that, yeah. So the other things I wanted to mention, I'll be out of town next week. I have two very secret surprise special guest lecturers arranged. One of these lectures will just be a continuation of the standard course material. The other will be a super secret surprise on a topic of interest outside of, I would say, maybe the standard course of a traditional first semester quantum field theory class. I did miss one class earlier in the semester, so I did want to schedule a makeup time, or a time to do that. What I was thinking was the following. Ostensibly the last day of classes is December 2nd, which is a Tuesday. Should we just extend that and have another lesson, a final class on December 4th, which is the Thursday? So nominally after classes have ended, but it would be keeping to the same Tuesday-Thursday schedule. Does anyone have a problem with that? Do you guys know your final exam schedules yet? Those of you who are taking finals, which is probably just the undergraduates, more or less. Does anybody know any final exam schedules? Yes.
For me and many people in degree,
Yes.
we have, I think, one at the very beginning, first week, and then you have three in the last week.
And the first week is what? Is the week of...
December around 8th.
Okay, right. So if I remember correctly, you get several days off. Like the last day of classes is December 2nd, which is a Tuesday, and then you get the rest of that week off, and then you have exams the following week. All I'm proposing is that why would you need that week off? So what I was proposing is that we have a special makeup lecture on December 4th, which is nominally after classes have ended. And in a related subject, we should schedule the final. So as we discussed in the beginning of the class, the final will be a 24-hour take-home. It'll be roughly typical in style to a problem set in terms of the kinds of problems I'll be asking. It'll probably be a little easier than a problem set, reflecting the fact that you only have 24 hours to do it. So maybe what do you feel about, I would also think that that week before the official start of exams is a good time to schedule that. So for example, if we're having a lecture on that Thursday, the 4th, I could give out the problem set at the end of that lecture, or the final exam at the end of that lecture. So that would be at 5:30 p.m. on the 4th, and then you could turn it in on 5:30 p.m. the following day. That's a little inconvenient because then you may feel the need to stay up late. So we could also schedule it some other time. You want to hand it out Friday? I could hand it out on Friday and you could hand it back on Saturday. That's fine with me. It's just a little inconvenient for people who might not want to come to campus on Saturday to turn it in. The other thing we could do is we could hand it out like at noon on Thursday, and you could turn it in noon on Friday, and we could have the makeup lecture like on Wednesday or something. Does that sound, does anybody care? Yes. Oh, we do have class on the 4th. Oh, okay. Well, I guess that's not going to be a makeup lecture then. Okay, For some reason, I didn't have that on my calendar. Okay, well, what time, should we schedule a makeup lecture like, I mean, if we schedule a makeup lecture like on a Monday or Wednesday at the same time, 4 p.m., how does that make people feel? Like Wednesday, 4 p.m., are people free? Okay. Quantum theory. No, you don't have quantum theory then. That's 11 a.m. I know because I just taught it. Sorry, what was that?
Wait, 4 p.m.?
4 p.m. on Wednesdays? Oh, is that quantum theory? Oh, you're right. I lectured yesterday on that. Sorry, I thought it was a different time. What about a different time, like say 2:30 on Wednesdays? That conflicts with anybody. 1 p.m. on Wednesdays? Conflicts with nuclear. This is the problem. There's 11:30 a.m. That conflicts on Wednesdays. What's that? Grad seminar. 10 a.m. on Wednesdays? Grad seminar at 11. And are Mondays the same conflicts?
You should check the week though, because the scheduling plans kind of catch you.
Okay, let's talk about Mondays. Mondays 10 a.m.
Which week? Depends which week.
Okay. Okay, how about Mondays 11:30? No, we have our seminars. Mondays 1 p.m. Nuclear again. Mondays 2:30, you probably have that same class. Mondays 2:30? Very early universe. Mondays 4 is guys class. Fridays. Fridays is good. Friday at 4, no, the colloquium's at 3:30. You can't really cross schedule against the colloquium. Friday 10 a.m. Everyone's free Friday at 10 a.m. Okay, good. So let's schedule a makeup lecture not next Friday, but the following Friday, which would be the November 28th. Does that sound good? Is everybody happy with that? Friday, November 28th, 10 a.m. Okay, perfect. I'll let you know where it's going to be. Probably won't be able to be here. It'll probably have to be in some other room. The scheduling of the final exam, we could hand it out on Friday, December 5th, and you could turn it in on the Saturday, or we could do a Thursday to a Friday, or Wednesday to a Thursday. What do you think? Does anyone have a preference? Should I just choose whatever's most convenient for me? You like turning things in on Saturday. Okay, so we'll pick it up Friday, December 5th, midnight? No, noon, to Saturday, December 6th, noon. Okay. Yeah, just a word, don't worry about the final exam. This is supposed to be a relaxing adventure. It's supposed to be a chance for you to learn things, right? This is not, my goal is not to torture you. That's merely a happy side effect. No, I'm joking. No, just don't worry about it. Just don't worry about it. Just don't worry about it. That's my advice. Yeah. Good. Any other questions? Yes. Topology exam is 9 a.m. on Monday. And what was your, and that means noon on Monday to noon on Tuesday. Yeah, I'm worried that if we get into the following week, other people have exams that Monday and Tuesday. Do other people have exams? Does anybody take exams in this class? I don't know. Not really, right? Yeah. I mean, I do know that some people are headed out of town that week. And so having it done by that Friday, Saturday is somewhat preferable. You want to do it before, like Wednesday or something? Wednesday to Thursday? The problem is that you guys all have other classes and stuff, I would assume. That, I can't schedule, I don't want you to skip guys' class, right? Yeah. Yes. If that's a normal, I'm told that that's a normal class. Ah, good. Okay, that's why I didn't have it on my calendar. Right. It's this confusing thing where there was a Monday that was canceled. Some Monday was a holiday, so the 4th of December is a Thursday, but the schedule on the 4th of December is a Monday schedule. That's why I have. See, I knew I knew that when I wrote my when I made my calendar, I checked these sorts of things. Okay. So yes, we don't have class on December 4th. We do not. I mean, we could schedule our makeup class on December 4th, but then what do you guys? Then guys' class will be meeting. So yeah, okay, good. We can't do that. Sorry, this is getting very complicated. Let's do something simple like quantum field theory. Okay. So the final exam scheduling. I mean, I probably don't want to do it like that Wednesday, Thursday, because people will have classes and stuff. So yeah, so we could either, I guess we could do it the following Monday if you guys prefer. Should we take a vote? I don't actually really care. Should we take a vote? Who wants to pick it up Friday, December 5th, as opposed to Monday, December 8th? So raise your hand for Friday. 1, 2. Vote. Now, if you want to pick it up Friday, December 5th, as opposed to Monday, December 8th. Who votes for the 5th? Okay. Were you raising your hand? Okay, 1, 2, 3, 4. 4 people? Okay, who votes for the 8th? 2. Okay, sorry. December 5th. Yeah. This class is not a democracy. It's a dictatorship, but it has the veneer of democracy to make people feel like they have some control. Okay, good. It's very useful. Okay, any other things we need to discuss? Hopefully that takes care of all the admin. What's that? December 5th. Okay. Yeah. If it's desperately impossible, let me know. We can always make arrangements for individuals to take it at some other time, if there's some real conflict or something like that. Good. But you can always study for topology ahead of time. So there you go. Okay. So what I want to do today is continue with our discussion of spinors. So we saw last time that there are really the basic spinor representations of the Lorentz group fall into 2 classes, the left-handed spinors and the right-handed spinors. These are 2-component objects, meaning that these are quantum fields that are really a pair of functions that mix with one another in some interesting way under a Lorentz transformation. But these 2-component spinors, called Weil spinors, don't preserve chirality. And so if you want to construct an object which is invariant under parity, that is to say has both a chiral and an anti-chiral piece, a right-handed piece, and a left-handed piece, then you need to assemble 2 of these Weil spinors into a single 4-component object known as a Dirac spinor. So this is a 4-component object. So it's a set of 4 quantities, each of which are functions of space-time. And typically, I'm not going to bother to write the index on the spinor field psi. We're going to do our best to avoid that. When I need to, I may occasionally use matrix notation and write psi as a column vector. But generally, that won't even be necessary, and we'll just have to use context to tell us about the various, spinor indices that we're suppressing. Okay. So the equation of motion obeyed by a Dirac spinor is the Dirac equation. So, for example, an electron of mass m obeys the first-order differential equation, that is the Dirac equation, where the gamma mu's were given in a particular basis that we worked out last time, which is usually referred to as the Weil basis, are given by a particular set of 4x4 matrices that we write in 2x2 block diagonal form involving the Pauli matrices, sigma I, or if we want to summarize that a little more succinctly, we write that in terms of the extended Pauli matrices sigma mu, whose components, so that's a 4-vector of Pauli matrices. Sigma 0 is just 1, and sigma I is sigma I. And here we have a sigma bar, where the bar just gives you, so sigma bar mu is 1 and minus sigma I. And from this, so as one can check, and I invite you to do so, this is precisely the Dirac equation that we arrived at in the beginning of the semester when we tried to take the square root of the relativistic version of the Schrodinger equation. So, in order to describe this theory as this equation of motion is coming from a Lagrangian, we need to find a scalar that we can construct out of this Dirac spinner. And one of the things that we noticed last time is that if you want to construct scalars out of spinners, you actually need to be a little bit clever. It's not exactly the way that you would think that you could write it. So for example, if you divide this Dirac spinner into two Weyl spinners, a left-handed spinner psi left and a right-handed spinner psi right, so that psi, the first two components of psi are the left-handed spinner and the second are the right-handed spinner. And then you define psi bar to be the 4-component row vector, which is not the dagger of psi, but instead the dagger where you interchange the right-handed and left-handed spinners. Then the Lagrangian, whose minimization leads to the Dirac equation, is given by psi bar I gamma mu d mu minus m times psi. Okay. So this is a real Lorentz invariant scalar. So my goal today is just to spend basically the entire day investigating the properties of the Dirac equation and becoming familiar with the manipulation of these various spinor quantities. And then starting next week, we'll consider the quantization of the Dirac field before the following week moving into the full glory of quantum electrodynamics, which is the interacting theory of an electron and a photon. Okay. So, any questions before I continue? Good. Okay. So far, we've been working with Dirac spinners in a particular basis, namely the one where psi is given by the 4-component vector that's psi left on top of psi right. But we could always work in a different basis. Where, for example, you act with psi by some unitary matrix, and all of the results should be independent of your choice of basis. So it really is going to be very useful for us to develop a language where we can talk about spinners without ever writing things out in a particular basis. Okay. So the starting point for doing so is to note that the gamma matrices obey what is known as the Clifford algebra. Namely, that their commutator is proportional to the metric. So gamma 0 squares to minus 1 to 1, and the gamma i's square to minus 1. So in particular, when we change a basis, what happened there? blinking in a sort of alarming way.
It's usually green when it's on. It's red now. This is weird.
Okay. Does someone want to take a look at that thing and see if it's doing something funny? Boy. Can you just like restart it or something? Is there just a power button? Yeah. Huh. Okay. I don't know. I mean, I could try. I somehow don't think it's my computer. It looks like it's that projector. Okay. There was no luck with that then.
No, I pressed on and off and
Didn't do anything.
I gotta wait.
Yeah.
Where's the on?
There we go. Okay. Can you guys see that? It looks sort of dark. It's warming up. Okay, so you guys can see that more or less? Yeah, okay. Good. Okay, that was exciting. Okay, so when you make a change of basis where you multiply psi by some unitary matrix, then you'll be conjugating the gamma. You'll need to conjugate the gammas by some 4x4 matrix. But the point is that this Clifford algebra will still be obeyed. Okay. So in general, we really don't care necessarily about the particular form for the gamma matrices. Okay, still, okay, that looks okay. We don't care about the particular form of the gamma matrices per se. We really only care that they obey this Clifford algebra. Okay. And in general, depending on the sort of problem that we're interested in solving, it may be convenient to use a basis where the gamma matrices take a different form. So, for example, I described the gamma matrices in the Weil basis earlier in the lecture. We could also take what's known as the Majorana basis, or the Majorana representation of the gamma matrices. And this is not a representation that we're going to really be using in this class, but I'll just write it down for you. Just, okay, what is going on here? Okay, it's doing that weird blinking thing again. What's that? It turned off again. Okay, should we just give up on this projector?
That's just the way. Yeah, but it's like green on the one next to it. Really? It's like green on the one over to the rear left. Right there, it's green.
Yeah,
it's
the
on.
next button over blinks.
Yeah, there's another light that turns on.
I mean, should I just give up? Okay, screw it. Okay, I mean, should we just give up? I'm worried that this thing is just never going to get fixed.
I think it's too long. Before you
You think it's overheated? Okay, well, we could give it a try. Okay. Okay, so the important thing really is that our gamma matrices obey this Clifford algebra. So we already wrote down the form for the gamma matrices in the Weyl representation. So in this basis, gamma 0 was 0, 1, 1, 0, and, or rather I should just say gamma mu was 0, sigma mu, sigma bar mu 0. But we could also write down what is known as the Majorana representation. I guess I won't even bother to write down the representation explicitly. You could look it up in the book. But it's a nice representation because it has the feature that all of the gamma mu's are purely imaginary. So when you want to think about, reality properties of these various spinor representations, the Majorana representation is a very useful one to use. Okay. So, in general, what we'd like to see is how much we can learn about our Dirac spinors. That is to say, the solutions of this Dirac equation using only the Clifford algebra and not necessarily thinking about the particular representation. So what are some sorts of things that we might want to be interested in doing with these Dirac spinors? Well, the first thing that we should do is understand how a Dirac spinor changes under a Lorentz transformation. So remember that last time we decided that a general Lorentz transformation could be written in terms of 6 parameters. So you could write it as e to the I theta I j I plus beta I ki. So this would describe a Lorentz transformation, which is rotation by an angle theta I about the xi axis, and a boost with the boost parameter beta I in the xi direction. And what we'd like to understand is how these rotations and boosts act on this 4-component Dirac spinor. So we explicitly worked this out last time in the Weyl basis. In particular, in the Weyl basis, psi is just a left-handed spinor on top of a right-handed spinor. And we worked out explicitly how these left-handed and right-handed spinors transform under Lorentz transformation. And we saw that under Lorentz transformation, psi left picks up a factor of e to the I theta I minus beta I sigma I times psi left, and psi right transforms in exactly the same way, except that beta has changed sign, so that altogether we expect this 4-component Dirac spinor in the Weyl basis to transform like this. Or, in terms of an infinitesimal transformation, delta psi will be equal to I theta I plus I theta I minus beta I sigma I 0, 0 I theta I plus beta I sigma I times psi. So that's what we worked out last time under a finite versus an infinitesimal Lorentz transformation. Okay. All I'm doing here now is just rewriting this. But what we'd really like to do is find a basis-independent way of writing this so that we're not eternally writing out everything in terms of 4x4 matrices. So to do so, I'm going to introduce a clever trick So in particular, what I'm going to do is I'm going to define, so the gamma matrices have a vector index. So what I'm going to do now is define a tensor, something with two indices. It's also going to be a matrix, just like, so these gamma matrices have a vector index and are also 4x4 matrices. This sigma is going to be a tensor with two vector indices and also a 4x4 matrix. And it's going to be the commutator of two gammas. So it'll be an antisymmetric an antisymmetric tensor in those mu nu indices, and also a 4x4 matrix acting on the spinor indices. And then the point is that under a Lorentz transformation, you want to write the transformation property in a basis-independent way. It turns out that this quantity that I've written up here is completely equivalent to the statement that delta psi is, well, S mu nu delta omega mu nu acting on psi, where S mu nu is 1/2 sigma mu nu. And as usual, delta omega ij is just a fancy name for theta ij, the rotation parameters theta, and delta omega 0I is theta I. So it's just a short computation to go ahead and check that indeed this is the case. So remember that in general we write S mu nu as the symbol that describes the transformation properties of a spinor under a Lorentz transformation, in the case of a Dirac spinor in some 4x4 matrix. And it turns out that that 4x4, so it turns out that the anti-commutator of Dirac matrices is the metric, and the commutator of Dirac matrices, the sigma mu nu, is precisely the thing that tells you, encapsulates how a Dirac spinor transforms under a Lorentz transformation. And it's straightforward to go ahead and check this. So to check it, you could just go ahead and compute the commutators in sigma mu nu explicitly. So for example, if you want to compute, in the Weyl basis, the gamma mu's had this particular form, and so an Sij would be a commutator of gamma I with gamma j. So Sij will be the commutator of a gamma I with a gamma j, which if you work it out just looks like this. And then if you just go ahead and plug in the definition of omega ij, that'll give you precisely the transformation property of psi under a rotation. And likewise, S0I and the Weyl basis is minus I over 2 times the commutator of the gamma 0 matrix with the gamma I, which will be a sigma I minus sigma I. Okay, so this was all in the Weyl basis. But the advantage of this formula is that we've written everything in a way that is completely basis independent. So we checked this formula in the Weyl basis, but because at the end of the day we only wrote it in terms of the gamma matrices, it's a completely basis independent statement. Good. Any questions before I continue? Yes?
The previous lecture was written that the presentation of the Lorentz group acting on a fifth component indicated that a new matrix, our field, a new minus 1 equals lambda alpha beta equals
Yeah, sorry, I'm not quick.
From
Yeah, I'm not-
representation of the
Right. So remember that infinitesimally, so under a Lorentz transformation, psi of x goes to some unitary operator that depends on your Lorentz transformation, conjugating this field psi, and then infinitesimally, delta psi. So this then is described as an action in two different pieces. So one of the sort of trivial part of the action just moves that space-time point around. The non-trivial part acts on the index. Okay. And so the full action of a Lorentz transformation on delta psi is really the sum of two pieces. The first of which was that differential operator acting on psi, and the second of which is this matrix acting on psi.
just to make a connection.
Yeah. And so it's really, it's the second, so, as we did last class, I'm just sort of, ignoring temporarily this sort of trivial piece and focusing on this sort of more important piece. Good question. Any other questions? Good. Okay. So in general, what we see is that under a Lorentz transformation, psi goes to e to the I delta omega mu nu s mu nu under a finite Lorentz transformation. That's just a rewriting of this equation in basis independent form. Okay. So, what else can we learn about just using this Clifford algebra? So a lot of our class today is just going to be spent getting used to manipulating spinors and understanding a bit better this Clifford algebra. So, the first thing that you learn is if you just stare at that Clifford algebra over there, you see that among other things it tells you that gamma 0 squared is equal to 1, and gamma I squared is equal to -1. This means that the eigenvalues of gamma 0 are plus or minus 1. The eigenvalues of gamma I are plus or minus I. So in particular, this means that the gamma 0 matrix is going to be Hermitian, whereas gamma I is going to be anti-Hermitian. And indeed, if you look explicitly at the form of the gamma matrices in the Weil representation, a little more detail here. So gamma 0, 0, 1, 1, 0, and gamma I was 0, sigma I minus sigma I 0. So you can explicitly check for yourselves, using the fact that all of these Pauli matrices are Hermitian, that the gamma i's are going to be anti-Hermitian, whereas gamma 0 is Hermitian. Okay. So what can we conclude from this? Well, one of the things that we can conclude from this, so let's just work out this product. Gamma 0, gamma I, gamma 0. How do you do that? Well, you can use the fact that the gamma i's and gamma 0's anti-commute, and then gamma 0 squares to 1. So this is minus gamma I, otherwise known as gamma I dagger. And likewise, of course, gamma 0 times gamma 0 times gamma 0 is gamma 0 dagger. So if you put that all together, you see that conjugating the gamma matrix by gamma 0 is the same as taking its Hermitian conjugate. So why is that useful? it's useful because it means that if you want to conjugate not just a gamma matrix, but any product, if you want to take the adjoint of a gamma matrix, not just a gamma matrix, but any product of gamma matrices, all you need to do is conjugate it by the matrix gamma 0. So if we take that operator, SB nu, that describes the action of an infinitesimal Lorentz transformation on the Dirac spinner, then its adjoint is, a simple way of writing it is simply by conjugating SB nu by gamma 0. So that's actually a very useful statement. And the reason why it's useful is that it helps us understand how we can construct various scalar and vector quantities from spinors. In particular, because under a Lorentz transformation, psi goes to e to the I delta omega s mu nu times psi. From that, if you just take the adjoint of that equation, under a Lorentz transformation, psi dagger will go to psi dagger times e to the minus I s mu nu dagger acting on, so that acts on psi dagger from the right because we've taken the adjoint of this equation. And so among other things, you can see from this equation with delta omega mu nu, that because these s mu nu's are not necessarily Hermitian operators, psi dagger psi is not a scalar. So because the gammas are not necessarily Hermitian operators, the s's are not necessarily Hermitian operators. However, we can then use this fact, the fact that conjugation by gamma 0 is the same as taking the adjoint of any product of gamma matrices, to show that if instead we consider psi bar, which is psi dagger times gamma 0, then using this transformation property of psi dagger under a Lorentz transformation, we see that under a Lorentz transformation, psi bar goes to, well, psi dagger times this times gamma 0, and then you can take the gamma 0 through using this, and all it does is get rid of that dagger. So go to psi bar e to the minus I s mu nu delta omega mu nu. So that if you consider psi bar psi, then under a Lorentz transformation, this factor will cancel this factor. And so this product is invariant. So you see, just by using the Clifford algebra, we've learned why it is that the psi bar that appeared in the Lagrangian for a Dirac field is not the same as psi dagger, but rather involved switching psi left and psi right. So for example, in the Weyl representation, remember we had psi was psi left, psi right, and psi bar was not the adjoint, but the adjoint where you switched psi left and psi right. And what is gamma 0? Well, gamma 0 is the thing that'll switch the two entries of these 2 by 2 matrices of this 4-component vector. So that is otherwise known as psi dagger times gamma 0 in the Weyl basis. Okay. Any questions on this? So this was all something that we saw last time in a particular basis, but now we've managed to derive it all more generally just using the Clifford algebra. construct vector quantities. So for example, gamma has a vector index, and it's actually relatively straightforward to show that under a Lorentz transformation, this vector index transforms exactly how you would expect a vector index to transform, so that, for example, a quantity like psi bar gamma mu psi will transform as a vector. Quantities like psi bar gamma mu gamma nu psi will transform like a tensor, and so on and so forth. And so, because of Lorentz invariance, the physical laws have to all be expressed in terms of tensors. And so, when we express the physical laws relating, for example, gauge fields or Maxwell's equation in terms of tensors, we'll have to formulate it in terms of quantities like these. Any questions before I continue? Gamma matrices are something that you will learn to know and love. Well, at least you will learn to know. Love is a more ineffable quantity that's hard to predict. Okay. Okay. So we're going to spend a lot of time manipulating spinor indices. And so it's useful to develop a notation that will help us manipulate these spinors a little bit more quickly. So the notation that we often use when we discuss spinors is what's known as the Feynman slash notation. So if we have a vector, v mu, then we can turn that vector into a scalar that acts on spinors. So it has no vector index, but it now is a 4x4 matrix that acts on spinors. And we'll shorten that by taking v and drawing a slash through it. So, for example, the Lagrangian of a Dirac spinor is psi bar I d slash minus m times psi. The Dirac equation is I d slash minus m acting on psi is equal to 0. And all of the various terms that we will write down later on in this lecture involving the coupling of, say, an electron to the electromagnetic field will also be written in terms of this slash notation. Takes a little bit of getting used to. Just remember that every time you see a slash, that's no longer a scalar, but rather is an operator that acts on these spinor indices. Okay. So you'll need to take into account, for example, when multiplying these operators together, that because they're 4x4 matrices acting on spinors, they won't necessarily commute with one another. Okay. So now, just to get a little bit of practice manipulating spinors, what I'd like to do is I'd like to go ahead and study the Dirac equation in a little bit more detail and rederive a few things that we derived at the very beginning of the semester when we thought about the Dirac equation. But I'd like to rederive them all using this gamma matrix algebra. So the first thing that I'd like to do is I'd like to show that, as we found at the beginning of the semester, this Dirac equation is really the square root of Schrodinger's equation for a relativistic Hamiltonian. So in particular, if you take any field psi that is a solution of the Dirac equation, then you could take the Dirac equation and you could act on it with this operator. Okay? So 0 is going to be this operator acting on the Dirac equation, okay, just acting with this on both sides of that equation. So that is just expanding out this product. So you get a minus d slash squared minus m squared acting on psi. And what is d slash squared? Well, d slash squared is d nu, gamma nu. You can always write gamma nu as the sum of the commutator of two gammas and the anti-commutator of two gammas. You can then use the fact that the equality of mixed partial derivatives picks out only the symmetric part, the anti-commutator, and then you can use the Clifford algebra, which says that the commutator is proportional to the metric. So this term vanishes. This is just twice the metric. And you get the usual Klein-Gordon operator. So plugging that into this equation, you see that any spinor, which is a solution of the Dirac equation, is also a solution of the Klein-Gordon equation. Now, that's what the Dirac equation was designed to do for a living, at least when we derived it in the first part of this course. But in the most recent derivation of the Dirac equation, we just kind of guessed it as really the simplest equation of motion that we could write down that was consistent with special relativity, okay, because it was a tensor equation derived from a Lagrangian that was a scalar. And indeed, we see just given that principle, you get something which is a solution of the Klein-Gordon equation. Any questions on that? Okay. So the Dirac equation really can be thought of as the square root of the Klein-Gordon equation. And the idea being that in order to take that square root, you need to promote the various operators that appear in the Klein-Gordon equation to operators that act on an additional spinor index. So what we're really interested in doing is using this Dirac equation to describe the theory of electrons and protons, electrons and positrons. Electrons and positrons have electric charge, so they have to couple to the electromagnetic field. And we saw that the way that we couple fields to the electromagnetic field is by first finding a global symmetry of that field, which will be some sort of U1 charge rotation, and then promoting that to a local symmetry using the gauge principle. And that uniquely determines how the various fields should couple to the electromagnetic field. So remember, for a charged scalar field, we had a complex scalar phi and the action was invariant under phi goes to e to the I lambda phi, or e to the I alpha phi. And then promoting that alpha to a function, it became the gauge parameter, and then demanding the gauge invariance of the action uniquely determined the couplings of the theory. So what I'd like to do now is do the same thing to determine how we should couple this Dirac field to electromagnetism. So in particular, the first thing that I would like to notice is that if you just make a rotation, if you just multiply your Dirac field psi by an arbitrary phase, then what was psi bar? Psi bar was psi dagger times gamma 0. So that will transform with the opposite phase.
It's really only a matter of time before I trip on this.
And so we can couple this to an electromagnetic field by using the gauge principle, which states that we should promote alpha. Oh, so sorry, the first point that I should make, if it wasn't clear, is that the Lagrangian is clearly invariant under this symmetry, So if psi goes to e to the minus I alpha psi, psi bar picks up e to the plus I alpha psi, those guys will cancel. And we'd now like to take that global symmetry and promote it to a local symmetry. So we promote alpha, which was previously a constant, to some function of x. And we demand that the theory be invariant still under this transformation, where now alpha is a function of x. And we do this by introducing a gauge field, nu, the electromagnetic field, which transforms under a gauge symmetry with a gauge parameter alpha in the usual way. And the way that we obtain an invariant action is every time we see a derivative in the Lagrangian, we replace it by a covariant derivative, which is just d mu plus I times a mu. And remember, just as in the case of scalar QED, we introduce this factor of E as the electric charge, really just as a matter of convenience. So we really put a 1 over E there. So what does this mean? This means that we can write down immediately the Lagrangian describing an electron coupled to the electromagnetic field. And it's just the Lagrangian. Guess I forgot. I'll pull out a factor of I here. It's just the Lagrangian of the Dirac field where we replace the usual derivative by a covariant derivative. So here I've separated out the mass term. And then we add in the kinetic term for electromagnetism. So minus 1/4 F mu nu F mu. So this is really the theory that is going to occupy our attention for the remainder of the semester. You can see here that the only thing that happens when we gauge the symmetry to give the couplings of the electromagnetic field to the electron is we get a single interaction term where one photon can mix with an electron and a positron. And so it'll take us a little bit of effort, but what we're going to do over the next week or two is work out what the Feynman rules are, taking into account the spinor nature of the electron and the positron, and then we'll investigate various consequences of this for scattering processes and so forth. Just to summarize, it's important to remember psi here is a 4-component object. Every time I write a slash, I have a vector index that I'm contracting the gamma matrix to turn that into a 4x4 matrix. Any questions?
Maybe there's no answer to this, but why is there only one U1 gauge field?
I mean, there's no answer to that. You know, there's, I mean, there certainly could be other U1 gauge fields. For example, there might be another U1 gauge field out there, and none of the matter that we know and love is charged under it. Okay? Then we would have no way of interacting with it, aside through except through its stress energy. But we certainly wouldn't, you know, be able to interact with it quite very easily. So a deep principle. So let's put it this way. As far as we know, there's no agreed upon deep principle that fixes the matter content of the standard model, or the field content of the standard model. There are various conjectures, there's various attempts, but grand unification, for example, is one attempt to understand the origin of the field content of the standard model in terms of more basic constituents. But nobody knows if that's right. So yes, there is not really a good reason for that as far as we know. Good question. Other questions? Okay. So let's just go ahead and write down the equations of motion that follow from the Lagrangian of quantum electrodynamics. So the Dirac equation is just the usual Dirac equation, except that we have to include a correction term coming from the coupling of the gauge field to the Dirac spinner. And then, so this is the equation of motion you get if you vary with respect to the Lagrangian with respect to psi bar, set it equal to 0. There's another equation that comes if you vary it with respect to psi and set it equal to 0. That equation is just the bar of this equation, i.e. the dagger of this equation. There's another equation that comes when you vary with respect to the gauge field. That will give you Maxwell's equation. And Maxwell's equation says that the variation says that d mu f mu nu should be equal to something. That's something that we usually call a current. And what is that current? Well, you can just read it off from this equation here. It's what you get when you vary this with respect to a mu. So you get E times psi bar gamma nu psi. Now you can see why it was that I was so careful to mention that psi bar gamma mu psi transforms as a vector, because in fact this is just the current of the electron in quantum electrodynamics. And in fact, we can check that this is the conserved current associated with this global symmetry. So using Noether's theorem, remember Noether's theorem says that if you have some sort of continuous family of symmetries labeled by a parameter alpha, then the conserved current is just dl by d mu of the field times the variation of the field under that symmetry. Okay. We derived this in the first few weeks of our course. And then you can just compute this explicitly from the action. And what you'll get, well, the derivative with respect to d mu psi just gives you a psi bar gamma mu. And what is the infinitesimal variation of psi? Well, it's psi. And as usual, Noether's theorem only determines the conserved current up to an overall number. And that number we see is just the electric charge. Question?
Just a reminder, Noether's theorem cares about whether we have global or...
Right. So the point is that when you have a global symmetry, you have a continuous family of symmetries, and you have the charges associated with them, and the current associated with them. And then when you gauge the theory, that current plays the role of the current that appears at the source in Maxwell's equation. So this also happened for the scalar field. So for the scalar field, for the complex scalar field, you know, J mu for a complex scalar field involved the derivative of the field. So it's phi bar d mu phi. And here we see that for a Dirac spinner, you know, life is simple for spinners. The Lagrangian is only linear in derivatives instead of quadratic. And so there's always less derivatives that appear when you have spinners. So there's not even any derivative here. Just a matrix. Is this clear? Is this hopefully pretty clear? I mean, it does take a little while to get used to the manipulation of these spinners, but you know, once you get used to dealing with these gamma matrices, it's all very straightforward. Okay. There's one point that I want to make, just by way of comparison with scalar quantum electrodynamics. So one of the things that we learned in scalar QED there was a term in the action that involved a mu phi bar d mu phi. Okay. So an a mu j mu term in the action. The gauge invariance also demanded that we include a term in the action that looks like this. So some 4-point vertex where 2 photons turn into an electron positron. And we see that that was just an artifact of the scalar field theory. So for true quantum electrodynamics, where we just have a spinner, this quartic term is absent. And it really comes from the fact that the Dirac Lagrangian is linear in derivatives rather than quadratic. With something that's quadratic in derivatives, you would have to square this covariant derivative. You get 2 A's, you get more fancy couplings. But because we have something that's linear in derivatives, that means that the coupling of the electron to electromagnetism in quantum electrodynamics is precisely what you would have naively guessed. All you have is an interaction of the form a mu j mu in the Lagrangian. Questions on this?
Generally, the spin of the field and comparing the scale of the field, these of freedom are less in the scale of the field.
Well, I mean, we'll get to the counting. So maybe by the end of class today, we'll get to the counting of the number of degrees of freedom of a spinner. But, well, there's a sense in which, yeah, okay. A Dirac spinner has the same number of degrees of freedom as a complex scalar field. Only 2. We'll get to that. I mean, we'll get to that, yeah. I mean, so naively, of course, a Dirac spinner has 4 degrees of freedom. But we're going to have to be a little careful about how we interpret those degrees of freedom, because the equation of motion will remove some of them. Okay. Okay. So I'd like to go ahead and make contact with one other thing that we discussed at the beginning of the semester. Actually, what time is it? Almost 5:20. Okay. You know what? Maybe what I would like to do is I'd like to end by just discussing the solutions of the Dirac equation. So, as usual, we're going to study this quantum field theory by first studying the free theory, where we neglect all of the interaction terms in the Lagrangian. which means that we really want to study first the solutions of the free theory. So that is to say the theory of a spinner that just obeys the Dirac equation. And just as with the scalar field, what we're going to end up doing is we're going to write down a basis of these solutions in terms of plane waves. We're going to expand psi in terms of that basis. And the coefficients will then be operators. They'll be raising and lowering operators. And we'll build the states in the theory by building a Fock space using those raising and lowering operators, just as we did for a scalar field. There are going to be some subtleties involved with this, which involve the fact that psi is going to be a fermion, that is to say an anti-commuting field rather than a commuting field. So it'll have to obey fermionic statistics rather than bosonic statistics. That'll be sort of the primary subtlety. But aside from that, the structure of the space of states of a free Dirac fermion will be just as they were for a scalar field. So the first thing that we need to do is find the solutions of this equation. So the solutions are easiest to write down in terms of plane waves. So a plane wave solution is one where psi is proportional to e to the I px. So here P is P0 P vector, and P0 is going to be determined in terms of P vector by the usual statement that psi describes a particle of mass m. So P0 is the square root of p squared plus m squared. And then what I'll do is I'll choose the positive sign here. And then note that there are really two choices if you only choose the positive sign. Namely the one where I put a plus or a minus sign here in the exponent. So in order to write out the solutions, let's just go ahead and take this ansatz, plug it into the Dirac equation. And what do you get? Well, every time you take a derivative, that just brings down a factor of p. So the Dirac equation then becomes a matrix equation for this spinner u, this four-component spinner u. So each time you get, so each derivative brings down a factor of I times p, and so you get p slash plus m acting on u is equal to 0. P slash is a 4x4 matrix. M is the mass times the identity 4x4 matrix. Acting on this four-component spinner u has to be equal to 0. Okay? Everyone with me? So, naively, you might think that if you have a matrix acting on a vector equal to 0, that's usually only has solutions when the vector is equal to 0, unless the matrix has 0 eigenvalues. And it turns out that this 4x4 matrix has two zero eigenvalues, and so there will be two linearly independent solutions. So the easiest way to think about these solutions is just to consider the simple case where we're working in the rest frame. So let's consider, for example, the rest frame where p vector is equal to 0, so that the only non-zero component is just p0, which by this equation is equal to m. So what does this equation look like? Well, it's m times gamma 0 plus 1 acting on u is equal to 0. What was gamma 0? Well, in the Weil basis, gamma 0 was the matrix with 1's here, and the identity matrix is the one with 1's here, so that in the rest frame, the equation for u is just that this 4 by 4 matrix annihilates u. And you can easily see that there are two solutions to this equation. So the two solutions, I'll call them u sub s, where s is an index that takes two possible values. So for example, u1 would be, say, 1, 0, 1, 0, and u2 would be 0, 1, 0, 1. That would be a particular basis of spinor solutions of the Dirac equation in momentum space. So more generally, if you're not in the rest frame, there are two solutions. us of p and vs of p. So s takes two values. And the choice of what two solutions you choose is really just some choice of basis. So you should think about the two values of s here as describing two different types of polarization of the electron. Okay, not a polarization because it's not a vector, but it's very similar to the two possible polarizations of a photon, linearly polarized in two different directions, except they're a little bit like the polarizations of an electron. So there's how much time? I'm like more or less out of time. Okay, I'll take like just 2 more minutes. So there's actually a simple way that we like to characterize these solutions. So it's completely straight. So I wrote down these solutions for you in the rest frame. We know how these spinors transform under Lorentz transformations. So you could always do a boost to write these in an arbitrary frame. It's a straightforward exercise. Out of time right now, so I won't write it down for you explicitly. I'll just make one more final statement, which is that there's a very nice choice of basis for these two solutions of the Dirac equation in momentum space. So the choice of basis is found by defining an operator, S. And what does S measure? Well, S is going to measure the spin of this electron in momentum space, but it's going to measure the spin along the direction of propagation. So S is the usual generator of rotations. Okay. So SI is epsilon I jk, sjk. So S is an operator that measures the spin in the direction of motion, that is to say, in the p direction. And it's known as the helicity operator. And so one convenient basis of solutions to the Dirac equation are the eigenstates of the helicity operator. So one nice basis are the two solutions u plus or minus, where now here S takes two values, it can either be plus or minus, defined by S acting on U plus or minus is plus or minus U plus or minus. And it actually, because these are spin 1/2 particles, if you go ahead and work to solve out explicitly, you would see that there's a factor of 1/2. So the U plus or minus are helicity eigenstates of the helicity operator. And you should really view helicity as the spinor equivalent of polarization. So the polarizations of a vector are like the helicity eigenstates of spin. Just as a vector, as a photon can have two polarizations, X polarization or Y polarization for a photon moving in the Z direction, an electron can have two possible helicities. It can either have helicity up or helicity down. Physically, what does it mean? Well, you've got some electron here, and it's moving in that direction. Then the helicity up state is the one where the spin of the electron is pointing in the direction of motion, and the helicity down state is the one where the spin of the electron is pointing opposite to the direction of motion. So this is positive and negative helicity. Now, of course, helicity is just one choice of basis. So, for example, you could also choose a basis, where one had spin pointing that way and the other had spin pointing that way. Just like for a photon, you could always work with circularly polarized light instead of linearly polarized light. But usually what we'll do, if we find the need to work in a basis, we'll use the helicity eigenstates. And so now, to quantize the theory, we just need to expand psi in this basis of helicity eigenstate plane wave solutions. And the coefficients in this expansion will be operators. They'll be the operators that create and destroy electrons with positive and negative helicity. So this is where I wanted to stop. But let me see if there are any questions. Absolutely, absolutely, absolutely.
Helicity is not one thing, right? It's like you boost forward, and like at the foot, like you're going front, upward. So is that useful to have spaces that's not one straight?
Okay.
Because when you're going faster, the velocities.
Yeah. I mean, you have to be a little careful because, so for example, if you go on a frame where the direction of motion changes, you also need to take into account how that Lorentz transformation acts on the spin. So it's a little hard to see, but I claim that if you do that at the end of the day, you'll find that helicity should be a Lorentz invariant function. And one way of saying this is a kind of nasty argument, is that Helicity eigenstates take discrete values, and you can't have a discrete function that's a continuous function of continuous variables, like boost and rotation parameters. So things like parity and time reversal can interchange Helicity eigenstates, but any continuous transformation cannot. That's an awfully slick answer. It would be much better if one could, and one could also just presumably work it out from the transformation rules.
So the spin flips.
That's right. That's right. It's a little, yeah. I mean, I claim that if you just take this operator, and you know how S transforms under Lorentz, you know how P transforms, go ahead and see how it transforms, and I think you should find that this is a scalar operator. Yeah. I mean, it's a little hard. It's a little confusing because I haven't written it as a 4-vector dot product, but as a 3-vector dot product. So, okay. So, we need to, one needs to be able to take some care when you understand how it works out. But, I claim that it should be a concern. Yeah. That's right. I mean, I guess I would say that this operator is sort of strictly speaking not defined for an electronic rest.
But it is a continuous transformation from this way to the
Yeah, I guess
way
that's
to
true.
the
That's a good
right.
point.
So what happens when
Yeah, okay. Yeah, that's a good point. Okay, I'll have to think about that. Yeah, let me punt on that question. That's a good point. I mean, you have to be a little careful because if you try and define this operator for an electron at rest, you have to divide 0 by 0. So you have to be really, let's put it this way. You can't define the helicity for an electron at rest, but you can define it for an electron that is moving, and then you can define its limit for the electron at rest by taking the limit where p goes to 0, and you'll get one of two possible values. But that value is determined by demanding that this is a continuous function. Does that argument make sense?
Well, it sort of goes to the
That's right.
with the previous question.
That's right.
Also, if it
Yeah.
is-
I mean, strictly speaking, this definition fails to apply in the rest frame. It applies in all other frames, and so you define its value in the rest frame to be, let's put it this way. In the rest frame, I just had to choose an arbitrary basis. In any other frame, we could really, I really want to define its value in the rest frame in the two Helicity eigenstates by taking this. Okay, so let's see. Hopefully the projector will be fixed by the time I come back. Okay, thank you. Oh, there are problem sets here for you to pick up.